Assalamualaikum. Welcome again to our online class. So we continue our chapter 3, which is the Bipolar Junction Transistor part 2. The course outline for this lecture is DC biasing circuit, which are the phase bias or base bias circuit, emitter bias circuit, voltage divider bias circuit, voltage feedback bias circuit, and the last part is the miscellaneous bias circuit. Introduction to BJT biasing. The goal of amplification in most cases is to increase the amplitude of an AC signal without altering it. Look at the figure A for the linear operation. The larger output has same shape as input except that it is inverted. Okay. For a transistor circuit to amplify, it must be properly biased with the DC voltage. The DC operation point between saturation region and cut-off region is called the Q point. The goal of biasing is to set the Q point in the active region, and it does not go into saturation or cut-off when an AC signal is applied. Look at the IV curve here. So the Q1, Q2 and Q3 located at the active region. With a good Q point established, an amplified signal at the collector of the transistor swings smoothly without exceeds the limits of operation, which is the saturation and cut-off region. However, applying too high of AC voltage to the base would result in driving the collector current into saturation or cut-off, resulting in the distorted or clipped waveform. The figure shows the phase bias circuit. It is the simplest DC bias configuration. For the DC analysis, we can replace capacitor with an open circuit because the reactance of the capacitor is become infinity. This type of circuit is very unstable since the beta changes with temperature and the IC. Base biasing circuits are mainly limited to switching application only. In the base circuit, by applying the KVL at the BE or input of the loop, we can get the VCC minus IBRB minus VBE equal to 0. Therefore, IB is equal to VCC minus VBE divided by the RB. So, we can calculate the IC, which is equal to beta IB. By applying the Kirchhoff voltage law at the CE or output of the loop, we can get the VCE equal to VCC minus IC RC. Therefore, VCE is equal to VCC minus IC RC. Since the VE is equal to 0, so VBE is equal to VB and VCE is equal to the VC.